Swayam Prabha. Digital India. Educated India.
Okay, I think we'll get started again. So now we're getting into business. We have roughly an hour and 50 minutes, more or less. Again, maybe I'll do a 5-minute break at some point for you to ask questions. But yeah, let's get into phase field fracture. So I think the first lecture, the objective was for you to, refresh or get introduced to basic fracture mechanics concepts that you will see are critical in understanding phase field fracture modeling. And now we'll get into, slowly introducing. I think some of you are familiar, but most of you have an interest, but are not familiar with phase field fracture. So I want to go slowly through each of the steps, and so making sure that you get a full understanding of the technique. So yes, from Intro to L03, we'll see how far we can get. A few years ago, I was asked to give a plenary or keynote lecture at a workshop, and they were very interested in phase field fracture, and they wanted me to talk about that. So I collected this information when I look in Google Scholar for phase field and fracture, and I started in 2010. 2010 was more or less, phase field fracture it's a bit older than this. But 2010 was when Christian Mie published some seminal papers that made the implementation much easier and more robust. So it's when it became particularly popular. The classic long paper by Bourdin, Marigo, and Frankfurt goes to 28. The original goes to 1998, Frankfurt Marigo, but 2001, the first one, and then 2008 was the one where the long one, the book, where they published the book. And 2010 was when Christian Mie published those papers. So I think this is more or less the beginnings. As you can see, there were already some papers going on, but it's growing quite significant. This is a workshop that was run in 2021, I think, or maybe even the end of 2020, so it was not complete yet. And I didn't have the time to fill the gap here, but I'm pretty sure it's going in that direction. So I attended the World Congress in Computational Mechanics last summer in Vancouver, in Canada. And I would say 90 to 95% of the computational fracture mechanics talks were on phase field fracture. And we were just discussing over the coffee break. I did embrace phase field fracture quite significantly, but it's not because I'm one of the founders of the method by any means. As again, I joined the field years after the pioneers have already established this field. But it was more because I was impressed by their capabilities. So I'm, at heart, I get a computational fracture mechanics person. I did everything throughout my PhD, cohesive zone modeling, XFEM, continuum damage mechanics, remeshing. I think I tried everything. And I used to go to conference and I'll see people presenting something that looked very nice with XFEM, and I'll say, okay, I'll go home, I'll implement that code. And then I was able to reproduce those nice videos, nice colorful results. But then when I change something, nothing else will work, or I tried to extend in another direction, it wouldn't work. So when I did it with phase field, my expectations were low. I just saw a new method being presented. I went back home, I implemented quite quickly because phase field is very easy to implement, as you will see later. And then I saw, not only I could get those colorful pictures that my colleagues presented at conferences, but I could also change things and get nice results, and I could make it 3D, and I can extend it in multiple directions. And it was also very robust. So I was very impressed by this method, and I don't know what the future will bring, and I will be very happy to embrace a better method if there is. But I was very impressed. It has really opened new horizons for us in computational mechanics modeling, and it has really taken over completely the computational fracture mechanics community. It's now been implemented in commercial finite element packages, used by industry as well, and so on. So it is very popular, and you may wonder why is it popular. So there's a number of reasons. One of them is how it changes the way we understand interfaces. Because it's not only useful for fracture, it's also useful for other problems, and we'll discuss some of those later this week. So if we think of, for example, the idea is actually quite simple. So if you think of two faces, a blue and a red face, you can describe the interface in between as sharp and discontinuous, or you can smear that interface over a finite domain, so describe a smooth variation in the phase between the blue and the red ones, and use an auxiliary variable, the phase field, to describe that interface. So you will see here the phase field takes a value of 0 in intact material points, in blue area, which will be intact material points, for example, and a red of 1 in the red area, which could be fully cracked material points, for example. And then it will vary smoothly in between. So any interface, not only cracks, but in the case of cracks, you will have, the interfaces between cracked material and uncracked material. Blue will be uncracked material, red will be cracked material. So if you describe the interface like this, in this simplistic way, then you only need to define a differential equation for the evolution of the phase field, and you're able to track where your interface lies. And this kind of implicit representation of interfaces has many advantages. 3 that I always like to emphasize is that the interface equation is defined in the entire domain, so there's no need for any special treatment. Think of, for example, if you need to do moving boundary conditions, things like this. The interface is moving, you need to apply boundary conditions in your interface. That's a mess. You need to figure out what the hell it is. Here, you apply for the phase field is being solved in the entire domain. At some point, it will be 1. At some point, it will be 0. You know where your interface lies. Topological changes, such as divisions of merging of interfaces, can be naturally captured. So if you think of, for example, cracks branching, coalescence of multiple cracks, you don't need to come up with a criteria, what you do, where you have a crack tip, what it's going to do when it defines the next crack. All of these things are naturally captured into this framework. You don't need to do anything. You don't need to put any ad hoc criteria. It's naturally captured. And then one that we exploited quite a lot in my group, and here is the only area where I think I can claim some originality, is in the extending phase field to multiphysics problems. So the interface equation can be easily combined with equations describing other physical phenomena. So I'll show you examples of this. But I think it's fair to say that phase field has been a revolution in many areas of science and engineering. It all started in the condensed matter physics community, what is now by far the most widely used technique to simulate microstructural evolution and solidification. It is becoming very quickly the dominant technique in fracture mechanics, in computational fracture mechanics. And you can see why here, right? This is red color means crack, blue color means blue. This intact material is blue. This is the outcome of a simulation for a hydraulic fracture problem. So fluid-driven fracture, that's why you see such a complicated cracking pattern. And these are, by the way, results, I think, from Yvonnette's group. And you can see that very complicated cracking phenomena can be captured. Right? You have coalescence of multiple cracks, initiation of secondary cracks, crack branching, crack coalescence. It's really very nasty cracking business that before we had phase field, there's no way we could capture such a thing. No way. So it's really, you can see why it's becoming quite popular. And then we have recently shown us, but also a group in the US, another one in Hong Kong, that you can actually model corrosion with the same idea. So we will have one lecture dedicated to this, but corrosion was considered always too complicated to be simulated with computers. I believe that we're at the time where we can finally do so, because we can use the phase field to describe the metal electrolyte interface, right? So if you think of this as metal in red, blue, seawater, you can see how the corrosion front is evolving. You can describe that with the phase field method, and I'll show you how to do that later on. But yeah, very powerful technique that is revolutionizing many areas of science and engineering. And I think the good thing in fracture mechanics is that not only it allows you to model complicated cracking phenomena, but it allows you to do so in a scientifically sound way. So in a way that is physically sound, that is in agreement with thermodynamics of fracture, with well-established fracture mechanics theory. So again, if we think back of Griffiths, what Griffith proposed, what we just seen in the previous lecture, is that a crack will grow whenever the energy stored in my material is equal or larger than the critical energy release rate, the fracture energy, my material toughness. This is what we just discussed, right? With this being the strain energy, the change in strain energy over this is the change in potential energy over a crack length. So this is exactly the same what we just discussed. And Francois Amerigo showed some years ago that you could express this energy balance in a variational form. And if you do so, you end up with this functional. And if you're able to minimize this functional, then you can predict the evolution of cracks as an exchange between fracture energy and strain energy, the energy stored in your material. So this is the same what we just been discussing before, just we're writing that mathematically as a variational principle. But the challenge here is that in order to minimize this functional, you need to know where your crack is. And we don't really know where my crack is. This is my crack gamma. I don't really know where my crack is. So this is where the phase field comes to a rescue, because the phase field is going to act as a marker. It's going to be like a damage variable. So it's going to go from 0 in intact material points to 1 in fully cracked material points. So then we can regularize this functional. This surface integral becomes a volume integral. And then we can easily, using finite elements, establish methods, we can easily minimize this functional. So we can predict the evolution of cracks as an exchange between fracture and strain energy. Elastic strain energy or strain energy and fracture energy. Key aspects to highlight here. One is that, of course, like any sort of continuum damage mechanics model, the phase field is like a damage variable, so 0 when it's uncracked material points, 1 fully cracked material points. So you are degrading your stiffness. When you have full damage, there cannot be any stiffness left, right? Remember the Griffith and the bar. The bar loses all load carrying capacity when it's fully cracked. So the same goes here. What form you use to degrade is, we normally use this quadratic form, but it's up to you. You can pick a different one. The other thing is that it's kind of a non-local continuum damage mechanics model. And that's the issue with continuum damage mechanics modeling, that first of all is it doesn't link to fracture as facial does, but also normally models are local, which means they are mesh dependent. Here, you get a non-local continuum damage mechanics model where you see you have a gradient, and because you have a gradient due to dimensional consistency, you bring in a length scale. And this length scale plays a role in multiple ways. We'll discuss them later on. But the key point that you need to think is that because you have a length scale, your results are going to be mesh independent, mesh objective. Your mesh has to be fine enough to resolve that length scale. We'll discuss that later. But if your mesh is fine enough to resolve that length scale, you are safe. So it's not like most continuum damage mechanics models where one engineer running the simulation with the same parameters but a different mesh, you're going to get different results than the engineer sitting next to it. And then, basically what it means when it comes to the strong form equations, the balance equations, is that you are solving for an equation for the balance of linear momentum. This is the standard, continuum mechanic treatment, Newton's second law converted into continuum mechanics, balance of forces. I'm ignoring body forces and so on. So basically you have, normally we just deal with the divergence of the stress tensor. Here, of course, my load carrying capacity is being degraded by the phase field. My stresses are degraded with the phase field. If my material is fully damaged, then it cannot carry any load. And then what you have is an extra equation, right? This is the differential equation that evolves the phase field. And you effectively see that what you have is a competition between the toughness, a material property that we can measure. That's the connection between the damage and the fracture. Everything relies on toughness, a material property that we can measure, and the strain energy density. And by the way, as you say, mathematicians have shown that, through gamma convergence, that this regularized functional convergence to the Griffith functional. So we'll do some tests, some numerical tests to confirm that this is the case, but in principle, mathematicians have shown rigorously that by solving this equation, you are going to predict that cracks grow based on Griffith's energy balance. When the critical energy is reached, when your stored energy equals your fracture energy, cracks will grow. And just by solving this differential equation, the quantity you are solving for is, of course, the phase field. That's your degree of freedom. So you have one extra degree of freedom in your equation. You're able to capture very complicated cracking phenomena without convergence issues in your original mesh and without any other special treatments. You can see here, this is, for example, dynamic crack branching. So it's crack branching occurring due to the application of a dynamic load. Because I'm applying a dynamic load, I get this kind of crack branching. And here summarizes why it has been, I guess, so popular. This slide summarizes why it has been so popular. So these are results, some from our group, some from other groups, some from IIT Madras, actually here. This is results from a collaboration. I'll talk about that later with Hrishikesh and Sundar Natarajan. Hrishikesh is an academic now. He was a student here, PhD student at IIT Madras, now an academic in another, I think it's an IIT, another IIT, yes, in India. But you can see why it's become so popular. So these are results shown for metals, for ceramics, for composites, for functionally graded materials. For a wide range of materials, not only you can capture very complicated cracking phenomena, you can do so showing a remarkable agreement with experiments. You can see here a thermal shock. I think it's in a ceramic, in metals. This is for carbon fiber reinforced composites. This is nuclear fuel pellets for nuclear applications. Very complicated cracking phenomena and an excellent agreement with experiments. I think that's the idea. So very powerful. It allows you to simulate things that we couldn't simulate before. And it's because it's based on well-established fracture mechanics theory. It's in well agreement with experiments. It's in good agreement with the physics. Yes? Yes, this is kind of a mixed mode type of fracture load where they see this kind of crack deflection. Yes. Yes. Oh, sorry. I should say, I will always use, thank you for that. I will always use red color for cracks, blue color for intermaterial. And so this is a... Exactly. You get this sort of crack deflection due to some sort of, I think, if I remember well, this was some sort of torsion, tension, mixed mode loading. But I'll show you another example now of crack twisting in a minute. But yes, you can capture, in principle, I mean, it's what fracture mechanics people will call the maximum energy release rate criteria, right? So cracks will take any trajectory they feel, any trajectory they feel will minimize the energy. So any trajectory that they feel is more energetically convenient, in a way, which is in agreement with what we see in experiments. And again, I'm not, what I want to clarify, when I used to work with other methods, when this crack reached this crack, I had to make a decision on what to do here. Here I just have a uniform mesh, fine everywhere. My cracks decide what to do by themselves, just based on that energy balance, energy principle. So this is the key takeaways. It's popular because it's computationally robust, and it's popular because it's physically sound. And computationally robust, I mean that damage is a complicated problem to deal from a convergence perspective. Because if you think of a standard, I would say backward-Euler type of approach, you're using Newton methods to get a solution to your nonlinear problem. You have a force displacement curve that is going up. Your Newton method is, you may get plasticity, so it's becoming nonlinear, but your Newton method still finds a solution. And then suddenly you go from a peak load to unstable crack growth. Your crack has dropped, and Newton method has to jump from here to something like a result that is very far away. And so damage mechanics is always a problem for convergence because it's difficult to go from something where you have a sample undergoing loading to something that cannot carry any more load. It's a big change in the solution. Just to make it simple, it's very difficult to handle. This method seems to be able to handle. I will discuss a bit that later on. But I guess the idea is that we can capture phenomena of arbitrary complexity. I cannot think of any fracture problem that I cannot capture these days with this method. 3D, crack branching, coalescence of multiple cracks, anything you throw at it, it can handle. And again, it's physically sound. Remember Griffith's fracture mechanics, stored energy versus fracture energy. And of course, this result not only valid for linear elastic materials. We'll discuss later what happens with elastoplastic. Remember that the toughness doesn't need to be the toughness of glass. It could be the toughness of any other material. And one point that I want to emphasize is this one here. So the method, as you will see later, gives you perfect agreement with well-established fracture mechanics theory. And we have found this not only to be reassuring, but also to be very powerful when it comes to dealing with industry, because engineers in industry, they are used to use standards that are based on fracture mechanics. So they like a method that gives them the same answer as the standards for the simple problems that they can handle with the standards. But then the method that they trust, because it gives them the same answers, they can be used to model more complicated scenarios. I think that's the takeaway. So let me start by looking into each of these things. First, how is it consistent with fracture mechanics theory? Let's look at this first. So mathematicians claim that it's consistent, but you can never trust them, so we're going to do a computational test as engineers and make sure that this is the case. So one thing that you can do is that I told you before, the displacement was related to the stress intensity factor. This is what we call the Williams solution. So there's if I think of a crack tip with a polar coordinate system, r and theta, I can express my displacement field as a function of the stress intensity factor and the coordinates. Which means that what people in fracture mechanics do often is what they use what they call a boundary layer model, and they take a circular model like this one, and they say this model can represent any component exposed to a given k field, because I can take my displacements here in the outer surface and apply a given k. So for a given k value and a given Young's modulus and Poisson ratio, I define for each of my nodes in my finite element model what the ux and uy will be to get this k value. And then I can just keep increasing that displacement, I can keep increasing my k. So in a way, it's a way of imposing a k. Right? You're imposing a k in your model. You could also have an infinite plate or very large plate and apply a load and use the equation that we discussed before. But anyway, this is the idea. And of course, there's a relationship between J and K, G and K. So it's based on this. This is for plane strain.
When you keep on increasing the K field is not applicable on some sides.
That's correct. So what we discussed before, so if you have here I'm just looking at linear elasticity, so it will always be applicable. If you have an elastoplastic material, you could have some edge effects, I guess, depending on the size of the sample. If you have an elastoplastic material, eventually the plastic zone will be so large that your K field will become invalid. Yeah.
What is the first terms of the infinite series of the Westergaard's?
Yes, so you have a T stress and other things as well. You could actually add them if you wish to. You could have a constraint effect, for example, with a T stress and so on. But in principle, this is the dominant term, yes, of the Westergaard series. So then if I apply this K field, what I want to see basically is, okay, that's actually when I do phase field. Now let's simulate the same problem. So people do this all the time, right? They apply a K field and they look at the stress fields and so on. Now we're going to solve the problem with phase field, and we're going to see, okay, will crack growth occur when K equals the toughness, or when, in other words, J equals the critical energy release rate? We'll do that. G equals the critical energy release rate. And this is what you see. So we did a finite element simulation. You see the crack growing. We apply this G field or K, and then we see how the G loading occurs as a function of the ratio of GC, the critical load. And this is as a function of, this is the phase field length scale that is constant. And what we change is the mesh. We refine our mesh. And you can see that initially we overshoot, but eventually as we keep refining our mesh, eventually we approach 1. So indeed, cracking starts. So my method is going to predict that cracking will initiate when my energy release rate reaches a critical quantity, when my stress intensity factor reaches a critical quantity. So in good agreement with fracture mechanics. What you can also see is that, of course, your mesh has to be fine. You need to make sure that you resolve your phase field length scale. And this is common to any other, I would say, damage or fracture mechanics model that is based on a fracture process zone. The moment you have a strength or a toughness, you have a length scale, a fracture process zone, and therefore you need to be able to resolve the fracture process zone. But you can see that roughly, when your element size is 6-7 times smaller than your phase field length scale, then you kind of get the converged result. And this converged result is in good agreement with fracture mechanics. We also saw if cracks will grow fulfilling this condition, that my energy release rate will be equal to a critical quantity. For that, we look into a double cantilever beam, where from beam theory, you can find the relationship between the energy release rate and the compliance, and therefore you can get a relationship between the energy release rate and the deflection. So we can apply a given deflection, and then we use 2 phase field models. I'll discuss that later on. But basically, we see that roughly we seem to be in good agreement. Cracks do grow, fulfilling that condition. So that's good news. I guess it confirms what mathematicians have told us, that phase field approaches do capture conventional fracture mechanics theory. Yes.
What you have showed now, so it's similar to smear crack approach.
Mm-hmm.
Where is the phase field as such? How is it different from the smear cracking approach?
You think for the one like Bazin, for example, or this type of models? So I think the main difference that I find with phase field and other, I would say, non-local continuum damage type of models like those, is that first, that is based on you'll see later the value of the length scale, but basically if we look at the equation, everything relies on it's basically non-local, so but other approaches are also non-local, but it's also based on fracture mechanics theory. So everything doesn't relate on some critical quantities that we don't understand, some parameters, critical damage parameters that we don't know. Everything is based on the length scale that I'll discuss later, and the toughness. And the material toughness is something, we have extensive databases of material toughness. And then so that's on the physics side of things. On the computational mechanics side of things, there's some benefits that are related to the fact that we are solving the damage as an independent variable and with a different PDE, because you add some flexibility on the computational side of things. I will discuss that later on. But so I would say simply the short answer is that it's more robust because you solve for the damage variable independently, so you get convergence much easily. And the other one is that it's connected to fracture mechanics. I don't have 4 or 5 parameters to fit. I just have one that is a fracture energy that I know before I run my simulation. So it's more predictive in that sense, I would say.
The damage variable, evolution of damage variables also need to have predicted before.
Yeah, so the damage variable here is the phase field, and the only thing that you're solving for is this equation, which is basically a competition between the energy stored, which depends on the strain energy density, on the mechanical fields, and the fracture energy, which is a constant that you know.
But the damage variable itself, how it evolves.
So we don't have a damage variable itself, it's just phase field is the damage variable. The phase field is the damage variable. So you are solving in a way for the damage variable. That's the idea. And yeah, I should emphasize, of course, the couplings here. So how I told you the phase field is the damage variable. So when the phase field equals to 1, so it goes from between 0 and 1. And then when it comes equal to 1, you of course degrade completely your load current capacity. How the phase field evolves between 0 and 1 is driven by this. So this is the strain energy density. Remember what we discussed about Griffith. You store energy in your material. When this guy is 0, phase field is 0. When this guy starts growing relative to your fracture energy, then eventually your crack starts growing and eventually becomes equal to 1. This is the idea. So that's the benefit. You're solving independently, so that has some computational advantages. And then the other one is that you only rely on one parameter that has a clear physical meaning that you know from a fracture test, and you connect very well damage and fracture mechanics. I think that's the key advantages, I would say. Versus non-local continuum damage mechanics. Okay, so there's one aspect. At this point, this is a perfect question for this point, because someone could say, okay, you said the advantage of this method versus, I will say, non-local. It's not that different from non-local continuum damage mechanics. It's much better than other computational fracture mechanics methods like XFEM and so on. But the main advantage is this connection with the physics. I don't have 8 parameters to feed that I don't know where they come from. It's just the fracture toughness. The other, and by the way, there's some, maybe I should have included some slides. So there's some blind tests done by Sandia National Labs, where they test. People can send their predictions. They do an experiment. They don't tell you what comes out of the experiment. They tell you what the experiment looks like. People send their predictions, and it seems that face field is really outperforming every other method, because at the end it only relies on this, quantities that we understood quite well. So it's quite predictive. It relies on only one parameter. But at this point you might say, okay, Emilio, this is not completely true. There's this length scale in there. What does this length scale mean? Well, the length scale is of course an indication of the size of the interface. It governs the size of the interface. So if your length scale is very large, if we go back to the very beginning here, this regime where you smear your interface, if the length scale is very large, it's going to be much larger. If it's very small, it's going to be much smaller. So it plays a role. And what should be the value of the length scale? Well, the value of the length scale, oops, I went too far. The value of the length scale is, of course, a fracture property. It's basically an indication of fracture per zone, right? So how big in reality, interfaces are not completely sharp. So you don't go from a material point that is fully cracked to one that is completely undamaged. You go from a material point that is fully cracked to something that has some micro cracks and something that has a few less micro cracks, and eventually to a material point in the continuum that has no damage whatsoever. So this is what we see in reality. So the length scale must be a material property. And it's an indication of the size of the fracture per zone. Which means that some materials will have a very small length scale, which means they will have a very fine mesh. So that's of course the challenge. But you see that you can see that basically that the length scale governs the strength of your material. So in a way, phase field introduces the concept of a strength through the length scale. And this is important because it means that, okay, we have two parameters, but these two parameters, you can think of them as GC and L, or you can see them as the material strength, the fracture strength, and GC. And both of these we know quite well. And you can get to this outcome very easily. So look at the phase field equation and consider the 1D homogeneous problem. So gradients go away. You kill this term, and you have this equation. So I'm just kill this term away. And now I can group the terms of the phase field, and I have something like this. Now I consider a 1D bar, again very simple 1D. Remember the strain energy density we just presented before. It looks something like this. So if I substitute in here, I get something like this. So I can get an expression for the phase field as a function of the Young's modulus and the strain. Again, Hooke's law, this is all linear elasticity, very simple 1D. And I know that the damage stress is equal to, the undamaged stress is of course equal to stress multiplies Young's modulus by epsilon, Hooke's law, 1D. The damage stress will be equal to epsilon Young's modulus and the damage, this degradation function that we took quadratic. So if I substitute in there, I get an expression like this, and if I plot that expression, it looks something like this. And if you take a one element model, what is also kind of 1D, and you run the simulation, you get the same thing. So those of you familiar with cohesive sum models or some of these damage models will also recall seeing something like this. It's kind of a traction separation law. So your stress increases almost linearly. Here you start seeing some nonlinear phenomena. Eventually you reach a strength, and then you get some sort of softening degradation until you get a complete failure. This is the idea. So it's kind of a traction separation law in a cohesive sum model. At the end of the day, if you think of a cohesive sum model, it's a very similar idea, right? You have a fracture energy, which in cohesive sum models is the area under the traction separation law, and you have a strength. And this governs the entire fracture process. And this is quite important because, as I showed you before, yeah.
Could you please explain the length scale? How does it work? Why is it material specific?
Yeah, so I think maybe to provide a bit more historical context. So when Frankfurt and Amerigo, when the mathematicians started developing these techniques, they were taking the length scale towards zero. They were saying, we do this gamma convergence study, and we take an infinitely small length scale, and then we show that it agrees with Griffith and so on. In practice, you can never take it equal to zero. First of all, because you need 5 elements to resolve the length scale. So if it's zero, then your mesh has to be infinitely small. So in practice, it will always be a non-zero value, but also it must be a non-zero value because in reality, interfaces are not sharp. If you think of how we describe at the continuum level damage or fracture, we have an area that is, if you look at a point that has a crack, there will be a point will be fully cracked, air. Okay, that's phase field equal to 1. But then eventually you will not jump immediately to phase field equal to 1 or to 0 because you will have material points which are somehow half damaged. If you look at a microscope, you will see that if you take an RBE, half of them is cracked, the other half still contains material. And so you have a progressive degradation. And this is what we normally call fracture per zone in materials. We know that the damage is spread over a certain region. So that length scale, since it tells me where my damage variable spans, it basically tells me how thick my interface region should be, is basically telling me how big my damage fracture per zone is. So it must be a material property because, for example, very brittle materials have a very small fracture pressure zone. Metals have a very large fracture pressure zone. Damage is occurring over a long area, where in brittle materials, it's a very small area where damage is occurring. And the good thing is that you can also, so conceptually, it comes as natural to think that must be a material property, that must have a size that is related to the material. What is nice to see is that mathematically you also see that, because by solving this 1D problem, or doing a one simulation with one element, you see that this is the behavior that you get. So the stresses and the strains, the relationship they get is something like this. So if I change my length scale, I'm going to get a different behavior here. So this is the equation, basically. This is the critical stress. This is this quantity. So but you can see it here. If you apply a strain, there's a length scale in there. So if you change your length scale, you'll get a different strength. And makes sense. Depending on your fracture pressure zone, your strength is going to be, in a material, is going to be larger, or said in another way. For a given toughness, if you change the strength of your material, your fracture pressure zone is also going to be smaller or large, right? If you have much higher strength, your fracture pressure zone is going to be smaller, and vice versa. So in a way, it makes sense. And then what this means basically for us in practical terms is that we can think of phase field being described by 2 parameters, length scale and GC, or we can think of GC and toughness. I like to think of GC and toughness because these are 2 values that I know quite well. I have an extensive database of experiments for all my materials of GC and toughness. And this is good because we saw just before, remember we were talking about this transition flow size. We said if the crack is big enough, we use fracture mechanics, so Griffiths. If it's small enough, then it's strength-dominated failures. So this means that basically phase field allows us to capture both, through this length scale, both toughness-dominated failures and strength-dominated failures. This is what you see here. So this is failure stress versus crack size. Remember, I showed you this before. When sigma equals sigma YL or sigma critical, then this is the strength-dominated failures. So in metals, sometimes we talk about plastic collapse, but you can imagine a ceramic. This is what happens when you reach a critical strength on ceramic. And then this is what happens with Griffith. And Griffith cannot predict what happens for strength-dominated failures because Griffith only has toughness. So Griffith, if you assume that you have a crack that is tiny, Griffith will tell you, oh, you need a super high load to get failure because otherwise you don't get enough energy. But we know that in reality, materials go from here to there smooth. We get toughness-dominated failures and strength-dominated failures. So these symbols that you see here, those are finite element calculations with phase field. So I took a plate with phase field. This is in this paper. I took a plate with phase field. I applied a load. I changed my crack size and basically computed when my crack grew. And you can see that it captures very nicely Griffith. That's expected. The mathematicians told us. We just saw it. We discussed it a few slides before. But you can also smoothly transition towards toughness-dominated failures. And this is exactly what we discussed before, the transition flow concept. And this is exactly what you see in experiments. This is for various ceramics. You can see you go from these toughness-dominated failures to smoothly these strength-dominated failures. And this is critical because this means that if I have an engineering problem, no matter what is the size of my crack, phase field is going to give me the right result. Because fracture mechanics will only give me the right result if I'm somewhere here, so if my crack is larger than my transition flow size. But phase field will not only give me those scenarios, but will also give me the right result in these scenarios. And this is good because, if I can handle tiny cracks and super long cracks and everything in between, then I don't need to think whether the method is valid or not. An engineer tells me I have this problem with this crack in this component. I don't even need to do back-of-the-envelope calculations to figure out whether this is larger than the transition flow size. I just run my analysis. I know what will come out of that analysis will be the right result. So that's the idea. So again, in connecting with this fracture mechanics.
For different AYW value, you calculate the sigma m, right? For this problem.
Say that again, sorry?
For every AYW value, you calculate the
Yeah, and in this case, I'm changing my crack size. But yeah.
So from there, you get the G value, right?
So in this case, good question. So what I'm doing here is I'm doing a finite element analysis where I have a plate with a given thickness and applied length. I increase my load. I pick a crack size. I pick a GC because that's an input to fracture, to the phase, right? A toughness. So I say I have a toughness of, and a length scale or whatever. I just give them. So by picking a toughness and a length scale, I'm defining my sigma C. So I know my sigma C. I don't change with length scale and toughness. I do all the calculation with the same toughness, same length scale. And then I change the crack size. And I apply load. I compute the failure load. And I plot it into this graph. And you can see that it agrees quite well. When I pick a crack that was very small, my applied load is in agreement with the toughness because you get an almost uniform stress field. When I pick a crack that is long enough, my applied load agrees with the critical load agrees with the one that will come out of Griffith's energy balance. the fracture mechanics.
How you calculate G value?
GC or G? Are you?
GC is a material property.
Yes. So here I'm. So this is kind of embedded into phase field. That's the idea. So whenever you're solving for this equation, basically you are at the end. What is G? G is an indication of the fracture driving force. So it's the energy stored in your material. So it's basically a regularized version of the strain unit density you could think of. So this is what is happening here. It's all embedded within phase field. I don't need to explicitly calculate G. This is what normally engineers will do before phase fields, or they still do, no? When they are looking only at crack initiation. They will calculate G or K, stress intensity factor, with a stress analysis, and they will then compare, and that will tell them whether a crack will initiate or not. Here I can model crack initiation and propagation just by having that G idea embedded into the phase field equation. So I don't need to calculate anything. I'm just solving this equation. I'm not doing anything extra. It's just solving this equation. I'll show you later how to do it, but yeah. Yeah, some question here and there.
Phase field variable, right?
Yes, sorry. Maybe I should emphasize it. The phi is the phase field variable, yes.
And it assumes only values between 0 and 1.
Exactly. It takes only values between 0 and 1. Yeah.
0 indicating completely damaged or cracked.
I'm using, every person uses a different approach, but most common, I'm using the most common terminology, which is 0 means no damage, 1 means completely cracked. In this way, when you come here, you see that when it's equal to 1, you have no load carrying capacity, right? Your stress equals to 0 because it's fully damaged, you cannot carry any load.
When you say completely cracked, how is the crack? Is it a complete width is propagated?
So this is solved locally. So every point, so for example, red color means phi equal to 1, blue color means phi equal to 0. So these points are completely cracked, which means that they don't carry any stress, but they will still, this structure will still carry some stress until you get a complete failure. Yeah.
It depends on the coordinates of the plate.
Yes. So this is a variable that we're solving. It changes in space, if that's your question. Phi is a variable that we're solving in space. You solve the phase field equation in the entire domain, and then in some values you will take value equal to 0 and equal to 1, and then it's changing its time over time.
So in function of x, y, z, and l.
Yes. It will vary across 3D if you want. Yeah. Thanks. And some questions? Yeah, or maybe.
Just a clarification about the single element simulation that you have shown.
Yes.
Can you talk about what was the initial phi value and how did you assign it? Because it wasn't clear.
Yeah. So this equation you can get analytically, as you see here.
Yeah.
You can also get it with a 1D element. You put a square element if you want. It could be 2D, but you make it 1D in the sense that it's all, you hold the displacement at the bottom, you apply the displacement at the top, and because you're not having everything is homogeneous, phase field is equal to 0 at the beginning, but it will just start evolving until it gets equal to 1. And then you can plot it, the phase field will do something like this. You go from 0 to 1, and the stresses will do something like that, like you see there. So it's a kind of a homogeneous problem, solving one element where you just don't impose any non-uniformity, or everything is homogeneous and you just pull. Yeah. I think there was a question there.
So say I want to repeat this for two materials, steel and glass.
Yeah.
And as I understand it, G is a natural consequence of the simulation of the deformation of the strain energy.
Yes. So GC will be the input. So you say for steel, I'll use, I guess 1,000 kilojoules per square meter. For the glass, I would use 3 joules per square meter. Yeah.
Then in that case, what would be the value of L?
So you will also have some sort of strength measurements of steel or glass. And what is sigma C in steel is a topic of high debate, because in brittle materials it's very simple to know what is the strength. In ductile materials you will say, is this the ultimate tensile strength? Is this the local fracture stress that you will get because of tractiality and different stress states? I'll discuss that a bit later on. But in principle, let's say you know what is your strength of your material. So since you know GC, you know Young's modulus, you know strength, you solve for your L. That's the idea. Thanks. Yes?
Usually in ductile materials, the fracture process zone is smaller. But if I talk about like quasi-brittle material or something like that, so in this case we have this sizable fracture process zone. So the L should be then, like whether the L should be higher, and can we take like some amount of elements inside L or something like that? Is there any relation between L and element?
Yes. So there's a bit of I would say debate on that. It's a good point. So I think people, for example, like Bazin would argue that fracture mechanics doesn't hold that well in concrete unless you have very large samples, for example, because they argue the fracture process zone, you got a lot of extensive micro cracking. There's a bit of debate on that. I'm not going to take sides. But in principle, you could have materials with very small fracture size, like in glass you don't see anything and then you see complete failure. Metals are a bit longer. In concrete, you may get a more spread of the distribution of the damage. So you could, that will give you the strength as well, basically. It will be connected to the strength. If you think of the strength, imagine that you have stresses ahead of your crack. Your stresses are going up. When do you start seeing macro cracking? Normally when your stress reaches some sort of critical strength, then you start seeing this macro cracking around. So you could in principle handle there are some other facing models, I think I get where you're going. There's other facing models which are trying to decouple the length scale to the strength. And some of them are quite heavily applied to concrete, so we'll discuss them later on. It's more what we call phase field cohesive model. I have a slide about those things.
Is there any relation between the element size and the length?
Yes, so the element size is what you see here. So we don't want to be here. We want to make sure your mesh is fine enough. Your results are mesh independent as long as you're resolving your interface. So your element size always needs to be small enough to resolve your fracture process on your interface. So here you see you need typically 5, 6, 7 times smaller. Yeah.
This curve, is it sensitive to the type of material? Or will it change if I use steel or glass?
No, it's roughly the same. It's all this only relies on, it's normalized, so it only relies on Young's modulus, but it won't change much. So what you find in this curve you can apply to everywhere. So if you say normally a rule of thumb that people will take is 5 times, if you use an element size that is 5 times smaller than the length scale, you are safe. The first papers of me and so on, people were taking 2 times, which is I guess somewhere here. I mean it's not too bad, but I will feel a bit safer if I'm in 5 times. So you still see a lot of people in the community taking an element that is half the length scale based on those MIA papers, but I will still say, based on this type of results, I'll feel more comfortable with 5 times.
And for audio analysis, you are actually computing L from the previous formula what you shown. The expression between.
Yes, I'll normally do that, yeah. And then of course a good question is, facing or the original facing model gives you to this formula. Is this the right formula? Is this the formula that relates, fracture process on to strength, or is there a better formula? Should I follow something like this, or should it be slightly different? I mean, that is up to grabs. It's a bit difficult to correlate. We know roughly it's the right approach, but there's other facing models like 81 facing cohesive model. The differences are small, but I'll discuss them later. But yeah, you could say every time I need to do it, I'll just apply this formula. Yeah.
This element size should be small in all 3 directions with the L5.
Yeah, if you don't know where your crack is, that's a good question. If you don't know where your crack is, then you need to put your mesh fine enough. So what this has led is to people use either adaptive mesh refinement, so they will just have a coarse mesh, but then they have some criteria to make the mesh smaller as the crack grows. Or what people will do is they will run one simulation with a coarse mesh. They will see more or less where the crack likes to go. Then they will refine that area, run another simulation, keep refining until at the end they have something that is, you do 2-3 calculations just to know where the crack goes. But for example, this calculation that I show you here my mesh is completely fine everywhere. It's just all squares everywhere. But I mean, so it comes at a cost. That being said, this runs in minutes in my laptop. So 2D simulations with hundreds of thousands of elements we can do these days quite fast. It's not a problem. But it is one of the bottlenecks of phase field. So, and of any other fracture problem or damage model that relies on a fracture process zone, which are the only physically based ones, because you need to resolve the fracture process zone. So if you are trying to simulate something that is gigantic and you have a tiny fracture process zone and you don't know where your crack is going to go and you want to model the propagation of the crack for the entire dam, then that's going to come at a cost. Yeah.
So if I'm doing simulation on a square plate of 1 mm by 1 mm and another simulation, let's say 20 mm by 20 mm. So as long as I maintain the L same, so will I get the same?
Yes, there could be situations where some edge effects will happen or things like this, but in principle, yes, that will be the same. So in terms of crack growth and so on, you get the same.
Always scale it down. So
Yes, exactly. Yeah.
my question is like, is this a 2D plate?
This is what you see in here, by the way. This is, this is here, right? So this is the same mesh. I'm just keep scaling down the mesh. So you see, you could get away with this, but you'll be paying an extra cost. Here, you should be fine enough. Yeah.
So if 2D plate, then it is okay. Suppose same plate we are considering 3 dimensions, and we know like it is uniform in thickness direction. So in thickness, we can say like less number of element compared to where the crack is propagating.
Well, you do. If you have the crack propagating through the thickness, you need to resolve that. So I'm going to show an example right now on 3D, so you'll see it. But you do need to resolve that. Yeah. Okay, so this is the example that we're going to show. So this comes at the perfect time. So there was a workshop last year. It was done by Purdue and Sandia National Labs. And they wanted to test sort of a new 3D printed rock. I think it was similar to ignium. They didn't tell the workshop participants what was this rock about. They said, we're going to 3D print a rock, and we want to test computational damage mechanics or fracture mechanics approaches. So we're going to give you some data. They gave us a uniaxial compression test, a Brazilian test, and a 3-point bending test. The Brazilian test was actually not valid in my opinion, according to some paper that we published recently, but anyway, that's not here or there. And then they'll say, oh, now after that, we'll give you a standard 3-point bending test, a Brazilian test, and a uniaxial compression test. After that, we're going to do tests where we are going to do 3-point bending with cracks placed in different locations, so you get some sort of mixed mode cracking. And we're going to do a 3-point bending test also with a crack tilted. And we're going to do both, we're going to see how the crack grows in 2D, but we're also going to do XCT scans. And we're going to record force displacement results. So they said, okay, we give you all of this, you need to tell us this. That's the idea. And of course, we don't have the luxury of calibration. We don't see the results. We send them our calculations based on this data and the geometry of the test, the blind test that we don't know the outcome. They send us the geometry, we reproduce in our computer, we send it, and then when all the teams have sent out their calculations, they'll say, okay, now we plot the final results, and you guys see how close your model was. That's the idea. This is what they call this round robin blind test. So that's the idea. So, and it was a material that we didn't know very well, because it was a kind of ignium type 3D printed model rock. We were not told which material it was. If they had told us, it would be even easier for us, because then we have a toughness and a length scale, a strength and a toughness. We would probably go to a database, say, oh, they use, I don't know, Portland cement, so, or whatever. So we can say, I have this strength, I have this toughness, I'm done. This one, we didn't know this material. But they gave us this 3-point bending test, so we only needed to calibrate with one 3-point bending test our strength and our toughness. And just the strength, actually, you can get from the Brazilian test. So, and then we try to predict. So this is the one at the bottom is the one they gave to us. And the other 3 is the ones they didn't give us. So they told us where the crack was, but we didn't know the outcome. So we run the simulations. We fitted our GC, and we know more or less for these rocks what is the value of toughness and strength, so we knew more or less where to be. But we also make sure to calibrate well to reproduce the force displacement response. And then we run these calculations. And you can see we place the crack in these are 4-point bending tests, because the cracks are located in different ways relative to this is the standard one, the one they gave us, where you have 2 pins here and 2 pins there, so you see mode 1. Here they change the location of the crack, so you see a bit of a franny cracking pattern, and then we predicted this force displacement curves. And we say, okay, we send that over, and they say, after everyone sent it over, they say, okay, we release the results. This is what it looks like. So these are the 3 replicate experiments. You can see quite a good agreement in terms of force versus displacement response all over the place. We were quite happy with our predictions. I mean, again, these are fully blind predictions. We have no idea about this data, but as you can see, we seem to be in good agreement. I mean, there's a bit of, we're not always in perfect agreement, but there's also a bit of a scattering experiment, so we were quite happy. And then they released the crack patterns as well. I don't know if you can see them clearly there, but again, what I believe is a very good agreement. In fact, you can superimpose them, and as you can see, we're getting a very good agreement all across the board. I mean, there's tiny differences here, but these are all crack deflections. We are not having any criteria. We just solve the facial equation. We don't tell where the crack has to go, just an energy balance that is embedded into that equation. The only thing we do is we solve a standard finite element problem with that extra equation. That's all. And we plot phi. I'm plotting phi, 0 or 1. And you can see the agreement is quite good. There's a question there?
Yes, wait. So the different colors of the graphs.
The previous one?
Yeah, what different colors?
Different experiments. They just run 3 experiments. So by the way, the black dashed line, this is our finite element prediction. We send this over, and then they told us this was the outcome of their experiment. Each of them is a different experiment. So there's a bit of scattering experiments, but the agreement I think is quite good.
In all the experiments, the weights are, the parameters are kept constant. The similar experiments.
Yeah. You're worried about why they didn't get that much reproducibility? I mean, rocks are complicated materials. This is a 3D printed rock. I'm sure there's a lot of things that are not macroscopic that are playing a role there. Yeah.
That's what I was about to ask. So since this is a 3D printed derivative of porosity, so
Yeah, so I think that probably since they follow the same printing protocol, the porosity is the same in all of them. So it would have been a challenge for us if they didn't give us a single test. They gave us one test. If they didn't give a single test and we say we are 3D printing this material, let's say whatever, Portland cement, then we will have data for Portland cement maybe in the absence of 3D printing, conventional methods. So we'll have to extrapolate from our toughness and strength to porosity influence toughness and strength. Since they gave us one and they printed all with the same method, then we could calibrate strength and toughness with one, and then we could predict the other ones. There could be, a bit of anisotropy effects. I mean, nothing is perfect, but for the time being, it seems that it does a good job, this kind of isotropic description. So the porosity will be embedded within the toughness and strength. I think that's the key takeaway. Okay, that's the results, so very promising. And then, as I told you, they also did one funny case, which is the one I'm showing here, where they tilted the crack to create a crack that will, that will rotate as the crack propagated. And they characterize that with XCT scanning. And they say, let's see how many of you can capture this. And by the way, other groups competed with this. There was another facial group who also got very nice results. And there were other groups using other techniques which didn't get that nice results. The papers are there, you can see. So this is the case of the 3D. Again, they didn't give us the result, but we ran the 3D case with the tilted crack, and we found this kind of funny crack behavior. So you were asking before, yeah, you need a fine mesh all over the place in this case. But I mean, this is something that doesn't take that long to run. So this is what we got, and this is what they gave us. So I'll show you here more clearly. Well, let me run it one more time. So we run a 3D simulation. Again, I'm not doing anything. I'm just running a 3D simulation, plotting phase field equal to 1, contours of phase field. You can see how it starts growing and how the crack propagates.
Is the simulation time for this?
So this was run in Abacus because we had no idea where the crack was going to grow, and this was something that was made. We didn't have the opportunity to recalibrate, right? We didn't know what the outcome was, and we wanted to be everyone knew about what we submitted and so on. So we wanted to be proud of ourselves. So we ran a very, very fine mesh everywhere just to make sure. So I think this one took, in a workstation, not high performance computer, but it took a few days, 5-6 days. So it was not super fast. But I mean, this is 3D calculation with quite a fine mesh, I would say. Yeah.
Can we say initially it started as a mixed mode crack, now it became a pure mode 1 crack, like made on top?
Yeah, cracks always like to go to mode 1 at the end of the day. So this is what we predicted, and initially it starts mixed mode because of the inclination of the crack. It's tilted, but then eventually becomes mode 1.
You don't have to perform an experimental proof for this.
No. So they did the experiment. They measure an XCT, and this is the MATLAB reconstruction of their XCT images. So this is the comparison between the experiment and the final element prediction. And I don't know if I didn't include the force displacement curve was also in very good agreement. And this is what they got out of the XCT. I mean, the XCT doesn't have the resolution of the final element model, but it does seem that I think they compare also, I'm only showing these graphical images, but they compare errors, and it was quite minimal. So it was actually capturing, they compared displacement fields, and it was quite minimal. So they agree quite well the shape of the crack, how it was tilted and growing. Yeah.
If you don't mind, may I know what is the tolerance limit for convergence?
Oh, this we use the standard, this was Abacus, the standard Abacus tolerance. We don't play with that, yeah. We touch it, we leave it as it is. Yeah.
It's a one-pass simulation or
It's a one?
it's not one pass, it's a convergence?
Oh, you think about stagger, single pass versus multiple pass? Okay, that's an advanced question. We'll discuss later on. But this one was a single pass stagger, but with a tiny increment, just to make sure that it was not deviating from the right solution. So you're probably right. If we had done a multi-pass, we'd probably be a bit faster. Maybe we could have done it in a couple of days with multi-pass. Yeah.
So this length scale parameter material property, if we calculate it from the formula that you have shown,
Yeah.
so like the value comes generally very high. Length scale parameter value.
Depends on your material. It could come high, yeah, depending on the fracture precision. Yeah.
So first we have to decide mesh size or length scale parameter, like which one first we should choose and then accordingly decide.
No, the length scale is a material property, so you don't have the freedom to pick that one. That one's, if you have a given material and you're going to be predictive, you need to take the value that comes out of the equation. And then what you pick is you pick your H. But I'll discuss now a few situations, because remember, the length scale, if you think of brittle materials, remember the length scale here. These results are influenced by the length scale because it's strength dominated. These ones are influenced by the GC. So if you have a problem where you have a very large crack, then you may not care that much about the length scale, because even if you don't get the right strength, you're going to predict, because your toughness is very energy dominated, you're going to predict the right result even with the wrong length scale. So I've seen on occasion people where they say, I know that I have a big crack. I'm very confident that I'm in the fracture mechanics regime. I'm dealing with an inelastic material with elastoplastic. I'll discuss a few items now. So then I say, okay, maybe I don't need to use the real strength because that will require me a very small element size. I want to use a bigger element size. You can use a slightly different one and you'll be okay. But in principle, the protocol should be, my length scale is fixed. I can play with the elements, and the elements, they need to be small enough. They cannot be that large. Yeah.
So the entire fracture process, like branching, for instance, everything is governed by just the minimization of energy.
Correct.
It is nothing else.
Correct. That's the beauty of the method. Yeah.
That's what phase field is bringing out.
Yes, exactly. That's the beauty of the method. Yeah. Okay, so what about plasticity at this point? You might wonder. Okay, when we discussed Griffith, I'm not sure if I made it very clear, but beyond Griffith, there was a man called Orwan. Griffith did all his stuff in glass, but there was a man called Orwan who, in the 40s, I think it was 1948, he published a paper where he said Griffith's approach also holds for plasticity, because he said, well, you just change the toughness, and instead of thinking of glass and something that is equivalent to the surface energy, you put any number you want there. And we discussed in the previous lecture that some materials have a very high value of toughness. So in principle, one could say, well, I could apply the same idea to plasticity, right? Thermodynamics must apply in not only in elasticity, but plasticity. So the energy balance must hold also in elastoplastic materials. That's true. So remember, the phase field is a competition, or fracture mechanics, a competition between a driving force, which is this G, or energy release rate, or strain energy density, versus a toughness, a material property, a material resistance to fracture. So okay, you just make the material resistance to fracture a bit bigger. What about the driving force? So you change something on the driving force. Before, we were using the stored energy, which was just the elastic energy. Remember, we plotted that bar, it was a triangle, elastic energy. Now you have a plastic energy. So what should you do here? So you consider the total energy, strain energy density, so you consider the elastic plus a bit of the plastic energy, only the elastic. Here in the literature, you find different people using different approaches. The approach that we champion is that we believe that, so there are some classic experiments by Taylor and Quinney in the 30s, where they measure basically how much of the plastic work is dissipated into heat and how much is stored in the material. And they figure out that under isothermal conditions, most of the plastic work will be dissipated into heat. So only 10% of the plastic work will remain stored in the material and therefore be available to grow a crack. As a result of it, what we do is we take this beta, we define a beta parameter that we take equal to 0.1. So we assume that 90% of the plastic work will go away, and 10% will be stored in my material and therefore available to grow a crack. That's the idea.
You also take into account the heat energy of the solid which is cracking in this energy minimization.
The what?
You also take into account the heat energy changes.
Yeah, so we don't model I'll show you some examples of thermomechanical fracture later on. But in principle, we don't. So at some point, you may wonder, when does the Griffith energy balance break down? What thermodynamics might always apply, right? So when is this? And you could have a situation where you have a lot of plasticity. There's also a lot of you're heating that area. So then, if you want to draw a full rigorous thermodynamics picture, you must build that heat balance into the picture. We don't look into that because we're not looking into those kind of problems. But I agree if you wanted to, and you could in principle, because you have this thermomechanical calculations where you're calculating where the heat goes and so on. But in principle, the only thing we need to know now here is what percentage of our plastic energy is being stored, plastic work is being stored in the material and therefore it's available. And we take 10%, and we believe that this is rigorous with thermodynamics of fracture and so on. I think that's the idea. So that's about plasticity. There's another element of plasticity. If you plot, so before, remember, I went to here, I was dealing with an elastic material. And I said, the critical, what happens here is I do a simulation, I apply a load that I then convert into a K, and then eventually I see that when crack initiates, my crack just grows because it's linear elastic material, it's brittle, mode 1, it's just going to grow all the way through. However, in an elastoplastic material, we know that metals exhibit a rising R curve, right? So the material, the toughness is not, if I plot applied K versus crack extension, this is what we call crack growth resistance curves, R curves. They just don't, the cracking starts with equal to 1, but they don't grow straight away. This is not what we do. If you plot an experiment, it will be the same, right? If you think of if you plot a metal, normally people plot K or J, could also be J. versus crack extension, it will look something like, it will start somewhere point here and they will do something like this. This is what it looks like. In fact, most standards like STM will tell you, oh, you need to pick the 0.2 value, so this will give you the toughness. Or it could be GC as well too. This will give you the toughness. So metals do exhibit that kind of behavior. So fracture will initiate at a given initiation toughness. This is typically a bit closer, like this. So metals do initiate at a given initiation toughness that the standard sometimes called K0 or J0. Metals do initiate there, but then they show a rise in our curve. So they have a toughening effect. This toughening effect comes from plasticity, of course, from dislocation activities. And you see this toughening effect in other materials. For example, carbon fiber reinforced composites, because of the fiber bridging the crack, you will see also this toughening effect. So this toughening effect is due to plastic work, and that is sensitive to the strength. So you see here, if I take different values of L, I'm considering different values of strength. Here they are plotted relative to the yield stress. And I'm not going to get into the details of the simulation. This was with strain gradient plasticity, it doesn't matter. But what you see is that basically, no matter what value of the length scale you take, fracture initiates at the same point. When the energy is, this is an example with a big crack, when the energy is big enough to reach a critical point. But the dissipation that you get, the plastic dissipation, will depend on the strength. If you have a very high strength material, you get a lot of plastic dissipation. If your strength is very close to your yield stress, you get less plastic dissipation. So this is what we expect. And in fact, there's a very seminal paper by Viggo Tergard and John Hutchinson in GMPS in 1992, where they did this kind of analysis with cohesive sum models. And you see that they get exactly the same, right? All start in 1, but then they change the strength in their cohesive sum model, and they see more or less plastic dissipation. So this is what you expect. But the key point here is that when you are dealing with an elastoplastic material, the value of L, before I said, okay, if you're dealing with a linear elastic material and you have a very large crack, then maybe you can take a L value that is more convenient for your mesh purposes, because fracture is going to be toughness dominated, fracture energy dominated, and therefore you don't want to use the real strength, because that might require you using a very small length scale and a very fine mesh. You want to do calculation fast, you're going to get the same result. Your result is not going to be very sensitive to L, so you may as well change the L a little bit. If you do that in plasticity, because the crack growth resistance, the R curve, is going to be dependent on your plastic dissipation, is going to have an effect. And that also answers the other question that we were discussing before. What is the strength? What does fracture strength mean in an elastoplastic material, in a metal? Is it the grain boundary strength, or is it the UTS? Well, whatever it is, here, if you have experimental data, like that one, you could actually calibrate your L to fit that experimental data, because the only thing that changes here is the L. All the other parameters you know. Cracking starts always at the same place. You know your fracture toughness. So the only thing that you don't know is how much plastic dissipation you have. And that will depend, of course, on your yield stress, your strain hardening exponent, but those things you know from a uniaxial stress strain curve, and your local fracture toughness, which you can calibrate with this. So that's another option. And then you know that you're dissipating the right amount of plastic. In this case, this is some sort of a fracture per zone length. It's a normalization, fracture per zone length. Yeah, from an energy, you can always take a fracture per zone length. So it's just you can forget about it. I can explain it later, but it's now a normalization parameter. But I'll explain later, yeah. And then remember the failure assessment diagrams that I showed you before. So what we see is that actually phase field can capture that elastoplastic behavior and can give you naturally those failure assessment diagrams. So remember, this is a key point similar to this one, right? So we said before, phase field will naturally capture, without you telling him anything about what is the critical transition flow size, how do you go from fracture toughness dominated failures to strain dominated failures. The same goes for plasticity and the failure assessment diagram. This is a paper that we just submitted recently, and you can see that we basically change the fracture toughness. So remember, the failure assessment diagram, if you are below the failure assessment diagram, you're safe. So this is you increase your load like this, and then eventually when you hit this point, you fail unsafe. This is what engineers use. They combine load with fracture ratio, and then if they are at the point here, they're safe, otherwise they're unsafe. What we do here is we run simulations where we increase your load. We start here, of course, at the beginning, load 0, our stress intensity factor is 0, our toughness is 0. But as we start increasing, then depending on what crack size we have or what toughness we have, we go through one path or the other, and then eventually we see failure. So we did that with a plate, and we calculate failure points, and we vary the toughness to span the entire regime. So for very brittle materials, for whatever yield stress we pick and so on, we're going to see failure driven by toughness. And for other for more ductile materials, we're going to be plastic collapse. And you can see that we get a very good agreement all across the board with the failure assessment diagram. So phase field can capture naturally this kind of elastoplastic phenomena. This is the idea. So all these J-integral ideas, all this elastoplastic behavior is naturally captured into phase field. And this is, again, quite convenient because whatever I do is going to be in agreement with the standards, it's going to be in good agreement with well-established fracture mechanics theory. And in fact, you can take a failure assessment diagram and do the same thing. So we can go from the transition flow diagram to the failure assessment diagram. You can see here, we did simulations. This is the transition flow size diagram, crack length versus stress. This is the toughness, strength-driven failures, toughness-driven failures. Again, phase field captures naturally the transition from one to the other. And then we can plot the same plots on an NFAD, and you can see that an NFAD basically is expanding this region here, making this region a bit longer. But again, this is, by the way, the same result that I showed you before, but now with an elastoplastic material. Okay, now I'm going to say, before we finish today, a few words on how to solve this problem. I don't know if I should stop. I think I can cover it in 8 minutes. Let me say a few words on how we solve this problem. So, I told you before, we just need to solve 2 equations. One equation is the standard equation that you solve every time you do finite elements. It's an equation where you solve for your displacement field. It's a balance of forces. The other equation is the phase field equation, and you solve for the phase field, which is your independent variable, your nodal degree of freedom, which is basically a damage variable, so to say. So, of course, there's 2 ways that you can think of how you solve this. You can solve them both at the same time. So basically, if I discretize my equation, I will end up with a system where you have a stiffness matrix and a right-hand side, and then I'm solving for displacement, and the same goes for the phase field, stiffness matrix, right-hand side. So the same way you derive finite elements. You actually don't need to do these things to implement phase field. I'll discuss that later, but if you imagine it the same way, this is the normal way you do finite elements. You solve for displacements. You will do the same for phase field. And you can solve them what we call in a monolithic approach, or fully coupled, where you solve both at the same time. You can see that it's a coupling, right? So here you use the phase field, which comes from here, and here you use the strain energy density, which comes from the displacement. From displacement you get strains, you get strain energy density. So you can solve them both at the same time. This is what we call the monolithic approach. This is very powerful. This is normally the way we solve our finite element problems because it's unconditionally stable. So it's a backward Euler type of approach, and this means that your results are going to be the same independent on the increment size that you use. That's the point. That's unconditionally stable. And then the only problem is that this regularized functional is non-convex with respect to both displacement and phase field. So it's not easy to get a solution. We have provided those codes, and you can try, and often we use monolithic, but often you get convergence issues. So a lot of the literature, what they use is what they call a staggered approach, which means that they solve one first and then the other. So imagine you solve the phase field first, you get a solution for phi, you freeze the phase field, you plug in your phase field, you solve the displacement solution, you get a strain energy density, you plug it in here, you solve for the phase field, and so on. That's the idea. You solve one and then the other. This people call segregated, staggered, or sequential approaches. And the good thing is that for a fixed displacement field, the regularized functional is convex with respect to the phase field, and vice versa. For a fixed phase field, the regularized functional is convex with respect to displacement. So this is very robust. You get convergence almost always. And this is the beauty of phase field. So by solving independently the displacement and the phase field problem, you freeze one relative to the other, you get this additional robustness. The problem with this approach, here you can also do what they call multi-pass or single pass. So imagine you freeze for a given load increment, you can solve for a given displacement, for a given phase field, you solve the displacement, you freeze displacement, you solve for the phase field, and then you move to the next load increment, or you could do another iteration. Okay, now I got a phase field, I go again here, I freeze my phase field, solve for displacement, I freeze my displacement, solve for the phase field, and I do another iteration. This is what we call multi-pass. So if you do single pass, you could lose the conditional stable situation, so you become, single pass can be a bit more robust, you'll get convergence more easily, but so if you deal with a very complicated, nasty problem where you're not getting convergence, you can use the single pass, and I don't think I've ever seen any problem where you don't get convergence with single pass, but anyway, we'll discuss that later. With single pass, you'll get convergence, but then you become kind of a forward Euler type of approach. So because you are freezing and jumping between increments, if your increment size is too big, you may be deviating from the solution. So it's kind of an explicit approach. So you may have to use very tiny increments just to make sure that you're not deviating from it. You need to do a time sensitivity study, basically. But what we have proposed in our group, and also another group in China, Monash, is to use a monolithic quasi-Newton approach, so the BFGS method. And when you do that, you combine the best from both worlds. You have a monolithic solution, so your results are unconditionally stable, and you get very good robustness and convergence. So let me show you some representative results. So this is a very classic example in phase field. Your material is linear elastic. You have a plate, square, with a crack, and you pull. This is linear elastic material, mode 1, so the crack is going to grow in an unstable way. Just sudden crack growth is mode 1 fracture in a brittle material, right? Unstable crack growth. So, and you see it here, right? So I'm starting to load, and then eventually, pop, my phase field becomes equal to 1, and you get complete failure. So here what I'm plotting is, first, look at the red at the right side. In red, this is the force versus displacement response. So initially, it's linear elastic, then eventually starts deviating a bit because of the damage, and then eventually, boom, you get the crack, the unstable crack growth event, and the complete drop in load carrying capacity. And of course, this is what the problem is for computational fracture mechanics modeling. You need to go from here to here, and that's complicated because you need to jump a significant amount. By the way, I may exceed a little bit the time today. I hope that's okay. Another day, maybe we'll end up a bit earlier. But I don't want to stop in the middle of this. So basically, you have a big jump, and this is what Newton-Raphson has an issue with, right? This is a nonlinear problem. You are somewhere here, and then Newton-Raphson needs to find the next solution, and the next solution is all the way here, and so Newton-Raphson is exploring this area and not struggling. This is why it's a problem. You can see phase field has no problem. So, and what I'm showing here in blue is the number of iterations, and by the way, each of these bars is a time increment. I decided to use 10 load increments. You can actually solve this problem with using 12. But I wanted to use more increments to resolve a bit nicely the graph. But you can use this problem using 12 increments. So this you can run, in my laptop I can run this, and it's on my website, so you can download it. You can run this in a few seconds. Maybe a few minutes, maybe 1 minute or 2 minutes. Maybe I'm exaggerating with a few seconds, depends on your laptop. But maybe a few minutes, 1-2 minutes. So it's a complicated fracture problem. When you have unstable crack growth, you can solve it, no convergence issues in a few minutes. And you can solve it with less than 30 load increments. You can do tests in your laptop with the code that you download. You can put 10, 12, you'll see that you get the right result. But basically, what is interesting here is that initially you see your increments are quite large, and you see that you get, in a couple of iterations, you achieve convergence. But in this critical point, you get 200 iterations to get convergence. And that's something very peculiar of phase field. Because normally, and in fact you need to tell Abacus, normally Newton methods, if you don't get convergence in 5, 10 iterations, then you lose all hope. Newton-Raphson is not going to find the solution. So normally Abacus actually, for example, will stop looking for solutions when it's 5. It will just start decreasing the load increment and doing other things. So you actually need to tell Abacus, hey, don't give him a bit more time. Give him a bit more time because he may find it. So that's the beauty, because you're freezing one field and then progressing with the other, you progressively approximate your solution. So that's quite interesting. But eventually, again, you can see you get a complete failure, 200 iterations, but again, eventually you get convergence. And anyway, it takes a few minutes, even if you have to do, because you only need to do 200 iterations once. And here you can compare with single-pass staggered solutions. So single-pass staggered solutions, so this is a classic experiment in the literature, a benchmark, numerical experiment. And you will see that some people, goes back to the Mie papers. In those Mie papers, the softening part looks something like this, a bit more progressive. And you may wonder, how can this be? This is mode 1 fracture of a linear elastic material. Fracture should be, completely unstable. You should lose current capacity. It should not be progressive failure. You can do it in the staggered approaches. If you use single pass, you can capture this kind of behavior because your results are mesh dependent, and you're freezing one field and then getting the other one, so you are slowing down. So you can see it here. If I use a staggered approach, single pass with 1,000 increments, then I get something that the convergence, the iterations are very low, maybe 2 iterations per cycle. But you can see that I'm deviating a bit from the solution. My peak load is higher because this is kind of an explicit approach, right? If I don't use enough increments, I don't get the right result. If I increase my number of increments to 10,000, then I do get the right peak load. I do get a bit more softening than what happens in reality. But a lot of people say, oh, okay, I can live with that because I only care about the peak load. So whether the softening, at the end what happens here is that my material cannot carry any more load, so I don't care. By the way, notice that even though the material has completely broken, we can still even capture, so this is quite nasty from a convergence perspective. Even though it's completely broken, we can still carry any load, we can still continue the calculation. So that tells you how robust the method is. But then eventually you see that if you increase the number of increments sufficiently, as with any other explicit method, you get the right result. And you see here total number of iterations. So yeah, monolithic, you increase slowly, then you have this big jump when you have 100 iterations, but then it's quite fast. The other staggered approaches, you have less iterations per cycle, but you need to use much more iterations to be able to get the right result. So I found these monolithic schemes to be, this quasi-neutral to be very powerful. This is something that is inbuilt into Abacus, but not in other places, so it's a bit tricky to use in other places. And one area where I think this can be a big difference is fatigue. We'll discuss fatigue. We have a dedicated 3-hour lecture for this. But fatigue is, maybe 1 hour and a half lecture, sorry. Fatigue is an area of significant interest since the first paper was published in 2020. This is from Laura De Lorenz's group. But basically the idea is you degrade your fractal energy with a fatigue degradation function. We'll discuss it another day. But here, it's important that you use these techniques because if you use a single pass staggered, you are kind of accumulating errors every cycle. So this little error that you don't care, in fatigue you do care because you're accumulating every cycle, and you can see here that you need hundreds of increments per cycle, and of course we're going to run millions of cycles. So basically these quasi-Newton monolithic solution schemes are a key enabler, I think, of phase field fatigue models. What else can you do? Well, you can do adaptive remeshing. So basically you can see, okay, there's things that I guess maybe the takeaway that I should say is that the method is very promising. It's in well agreement with well-established theory, not only fracture mechanics, but also strength-driven fractures. But you do have to pay a computational cost. Your mesh has to be fine along where your crack is going to propagate. So what can you do? Well, first, these monolithic solution schemes, in my opinion, significantly accelerate calculations because you can use 10 load increments to resolve your problem. So you can do it in a few minutes. The other thing that you can do is you can do adaptive remeshing. Again, this is work coming here from IIT Madras with Sundar and Hirshikesh. I must confess I've never been a big fan of adaptive remeshing because there's a cost associated with the remeshing, and because very often you know where your cracks are or you're going to grow, and if you don't know, you can always do a simulation with a coarse mesh. You see where your crack is going to grow, then you refine that area, and then that's fine. So you do 2 simulations, but if you have no clue where your crack is going to grow, I guess, and you don't want to run those simulations, this is not a bad way. But the idea is that, of course, depending on the value of the phase field, when you see that it starts to grow, you can make your element smaller, and then your crack propagates there. Yes?
This type of meshing I see is always rectangles in only one orientation. Which means a crack face is always a step staggered. Crack face.
But so in this method, you don't have to have full elements crack or uncrack. This is the problem with local continuum damage mechanics. Here is no local. So the extension of where the crack is going to be distributed depends on the length scale. And therefore, you're not going to have elements that are either fully a crack or uncrack. You could have an integration point that is fully cracked and another one that is not, in that sense. So you don't have a staircase. That's what I'm saying. So normally, when I mesh my mesh, I just use uniform mesh all over the place if I don't know where the crack is going to go. So what I would do if I were here, if I'm not using adaptive remeshing, I would use maybe a mesh like this one maybe, that I know is probably too coarse, but I'll put this mesh everywhere. Then I'll see that the crack is deflecting in that direction. So then I will use a mesh like this one basically over this square. In the second calculation, that will be the end of it. But you can also use these kind of techniques where you start with a mesh like this, and then depending on the phase field, you start making your elements smaller, 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 and then eventually you get the right result. Oh, I don't remember how many, tens of thousands, I guess. We probably start with, so you're increasing your number of elements. So if you're going to check in the paper, we tabulated everything. I don't remember by heart. Yeah.
Every element has the same number of nodes?
Every element has the same number of?
Nodes.
Oh, yeah. We use standard elements. All of this you do with the standard elements. You are solving for an additional degree of freedom in the node, but you can use standard elements for this. And there's tricks on how to do that. I'll discuss that tomorrow, how to implement this. Tomorrow we'll discuss all the implementation details. But yeah, these are all standard elements. So these, I think, are all linear quads.
One element is typically connected to the 4 elements on one side, 1 element on the other side. Some of the elements.
They're sharing nodes, yes.
So how does it work?
Well, you solve another degree of freedom, right? So it's similar to displacement. So you will get a value of the phase field in the nodes, and then you interpolate within your element. So similar to displacement field, any other quantity that you solve. Similar to temperature. Think of temperature. If you solve for temperature, it will be the same as you're solving an extra equation where temperature is varying non-uniformly in your component. Instead of temperature, it could be phase field.
So this remeshing is done at every step when the crack is propagated?
Yes.
So it will be like too much computation.
It carries a cost. And so we show in this paper, and everyone working on this adaptive remeshing area shows, or adaptive mesh refinement area, shows that it is competitive. but it's not as extremely competitive because precisely there's a cost of every time doing a remeshing, passing information from elements to elements and so on. So it comes at a cost. I'm just saying as an option. Some people are working on this. I haven't put that much effort in there because I see a lot of complication for small gain, but that's a personal opinion. Other people will think differently. There's a few items, but I think we're getting a bit late. I don't know if I stop now and continue to take it from here yesterday or tomorrow, or we continue a bit more and we finish a bit earlier another day. Let me see how many. Okay, I'll stop now because some of the aspects are interesting. So I'm going to stop now, and tomorrow we start with this before we get into computational. There were some questions, I think. Yeah.
For the real material, if the back propagates, then it will take the direction at the time of branching where the microcracks will be available. So in the case of F2 method, how we will implement this, that whether these microcracks or microbites are available.
So you're saying in the case that you have crack branching and microcracks initiating, how do you handle that?
Yes.
Yeah, so there's nothing. That's the beauty of it. You don't have to do anything. You're solving for the facial. So if energetically it's convenient that a crack nuke. So for example, let me take you some of the examples. So this one was from. You can see here. So it's energetically convenient for a crack to branch or nucleate or secondary crack. Look at this one is quite remarkable. This thermomechanical experiment. This is thermal shock. So you have something that is at a high temperature. You put it into a bath at room temperature, and then cracks initiate, and the spacing is related to the change in thermal load and so on. And you can see that the experiments in the model agree quite well. You don't have to do anything. You're solving a problem, and the energetics are such that you're going to nucleate cracks in multiple locations and that you're going to grow cracks up to a certain distance and so on. So you don't have to do anything. You just let it go, and it will capture that. That's, I guess, the beauty of it, that if it's energetically, the competition between fracture energy and stored energy are such that the loading pattern and so on should lead to multiple crack branching, that will come out naturally of the model.
Automatically, the physical model will take care of it.
Yes. You don't have to do anything. You just
It is having a good correlation with the actual physics.
with the actual physics.
Yes.
I mean, you can see it in these ones here. It's often difficult to do well-monitored fracture tests where you have a lot of crack branching and a lot of things, but you can see very well here that the agreement is quite remarkable. So I think it seems to be a very good agreement.
If I start a simulation with no crack, will I still get a convergence solution?
If you start with no crack and you start nucleating cracks later and so on. Yeah, this is the case here. So this one starts with no cracks. So yeah, we'll say a few words about nucleation tomorrow, but you can nucleate a new crack, and yeah, it will get convergence. There's no problem. The nucleation part is not demanding convergence-wise, but this is a good point to discuss tomorrow. The
Has to be a minimum solution that has to exist for this corresponding.
Yes, but you will find this. You can find the global minima. Yes. Yeah.
For the monolithic scheme, in the PFGS, what is the influence of the tolerance values? Is there any significant influence?
We use what comes in Abacus by default. So you don't have to do anything about that I mean, you're welcome to play with those things if you want, but you don't have to do anything special from your standard finite elements. It's fine. Sorry, one second. One thing that came to my mind, the line search. So when we start doing this work, we did it in Abacus because Abacus has it all implemented. So we just touch a button and said, oh, wow, this works so nicely, the BFGS. Then some people have tried since our paper to reproduce it in their own codes. And I was told a few groups have managed to get this very good behavior, but I was told that you have to do it exactly as Abacus does. So this particular BFGS implementation, and you need to put a line search, which Abacus has already inbuilt as well. So that's one aspect. Yeah. Thanks.
So FAD maps when put a plasticity, so it is valid for the room temperature. But if I want to do the simulation for the ductile material and the cryogenic temperature, so the governing equation will be valid or I need to change or some modification?
Yeah, good point. So we will discuss multiphysics problems, and thermomechanical fracture is one of those. It is true that most of the problems we deal with are isothermal. So in those isothermal, we say this beta. I mean, this Taylor and Quinney did experiments over a wide range of dynamic loads and temperatures. But if you take isothermal conditions and quasi-static, we know that only 10% of the plastic work will remain in the material. The rest will be dissipated. If you vary the conditions, either by changing the strain rate or the load, you may have to think of other parameter to put in there. Yeah. It might be that whether you put here 10% or 50%, it doesn't matter for your problem. But if you're interested, for example, in this kind of behavior, subcritical crack growth, where you get different arc curves, it can play a role. Yeah. Okay. Yes.
So this kind of thermal dispersion, isn't it a problem in that brittle fracture?
What is the problem in brittle fracture?
When we talk about plasticity, we're saying that only 10% is stored,
Hmm.
and remaining is dissipated into heat.
Okay, I think I get where you're going. So there's multiple ways in which the community has extended phase field. So phase field was initially proposed for linear elastic materials, and then it was extended in multiple directions. There's multiple ways in which the community has expanded phase field into the plasticity or ductile fracture regime. I'm telling you I'm a bit biased, of course. I'm telling you what my way and what I think is the best way. But there's other approaches. So other people have said, for example, maybe I should degrade GC with a plastic strain. Other people have coupled this with Gorson methods. I think in general, if you're talking about fracture in elastoplastic materials, this works okay. Not only for small scale yielding, where K dominates, but also for J. If you are talking about shear band localization, things like this, I think these other methods where maybe the plastic strain lowers the fracture energy, they seem to do a slightly better work. So if instead of fracture, you're thinking of more localization phenomena, it works a bit better in this other way. Yeah. So maybe I could include a slide of that on future days to show what other people are doing. So there are various approaches. Okay, if you have no more questions, thank you all for surviving so far, and I'll see you tomorrow morning. Thank you.
Clap for Emilio, he has been speaking.
Thank you.